Hello, everybody. My name is May, and I'm a master's graduate from the University of Waterloo in Systems Design Engineering. Currently, I am turning my master's project into a startup in using eye screening, making eye screening more accessible for everyone. If you're interested, we can talk later about it. It's called Napkin, because all great ideas start on napkins. So, about this paper, neuroscene representation and rendering. If you think about imagination is what makes us human, or is it? Can we teach machines to imagine? And that's really the idea behind this paper. Do we really need a whole lot of data to train CNN to be able to generate another perspective? So this paper was one of the top hits in 2018 by DeepMind. So if I were to show you an image, who knows where this is from? Nerves, right. But how did you know that? Right, you had this memory of it. But see, if I inputted this into a CNN, it would first go through the image in bounding boxes, try to grasp, okay, there's a person there, there's another person there. So we need a whole lot of images, right, to train this network to recognize. Now, if we want more granularity, we can probably get pose estimations, we can get gender predictions, but how does that really tell us what's actually in the image? What if I wanted to sit in the front row, because I was all the way at the back. What if I want to sit in the front row? What if I wanted to know who was talking? Oh, look, it's Jan LeCoultre. What if he was a keynote speaker? What if I want to know what he was looking at? He's probably looking down the aisle, right? So these are different perspectives that you can, or viewpoints, as I'm going to refer to them from now on, that we want to predict. So I want to be able to see what another perspective is looking at. And that's really the key of this paper here. So what does it mean to see? The plain man's answer is that to know what is where just by looking. By David Marr. It's a great book if you want to check it out. Vision. So we're not going to use real life examples for this experiment. They didn't use that, but essentially they used blocks or objects in a square room. So you have blocks, and if you see these two blocks, is it really 2 blocks or is it 3 blocks? And so you might need another perspective to answer that question. And this was taken from Society of Mind by Marvin Minsky. Great book again. Check it out if you have time. So the experiment really starts here. You have a room, you have a square room, you have a number of objects in the middle of the room. And you take different perspectives or observations of this image. Can you see my pointer? No? Okay, so you have the V stands for the viewpoint. It's not volume, just to clarify, it's the viewpoint. And you have 2D images. These are 2D images that you're putting in. It's kind of like if you took your smartphone and you took an image. Right, you're taking the image of the objects in the middle of the room. Now we have 3 images of the objects in the middle of the room. Great, now what? We can take these 2 images, take 2 of them, put it into a representation network. So we're making a representation of these images, these 2D images. And we're summing them up element-wise because we don't really care like the order of the images, right? The order doesn't really matter. So after summing them up, we input that into a generation network. Now we're going to be generating the viewpoint at a third viewpoint, the view at a third viewpoint. But now we have a ground truth of what actually the third person is seeing, right? We have that real observation over there. And now we're trying to generate the third view. How are we going to do that? So we have H here, different hidden layers of this generation network. And you have a latent variable with the Z is really you're just inputting some noise into this network so that not every time that it's a different thing that you're generating every time. And you're querying. Why it's called a generative query network? You're querying the generative network with the viewpoint or the position at which you want to see or you want to predict. So after putting in that V, you render, and then you get this you get this predicted view over here. So we have this predicted view, and we have that actual view over there. How similar do they look? What do you think? What do you think? Hassan, what do you think? They look pretty.
Hopefully similar.
What do you hope? Do they look the same?
Right now,
do they look similar?
I was given ground truth.
Right. You were. So does everybody get that?
So it's
Right.
supervisory.
No. So you're giving the ground truth. So like what actually is happening at the third viewpoint. So V3 is the third viewpoint, right? So that's what's actually happening, and then you are predicting what's happening, or predicting what you're seeing. So you take the difference between. So everybody get that? Everybody's on that page?
So I think then is it not fair to say it is?
No, it's unsupervised. So you
So
do
generating.
have the third observation, but during training you're just doing.
You don't have access to it.
You don't have access to it.
Gotcha.
No. Yeah. So we are holding out
'Cause
this
only-
part. So
yeah.
we're not taking this part in, but rather we're taking.
Yeah, that's why V1 and V2 are the only things input.
Do you compare them afterwards? Just to
Right,
see?
so
Yes.
now you're going to get the error, right,
Right.
between the actual,
Right.
the ground truth, and the generated. And then using that error, we're going to backpropagate through both networks to make them better the next time. But the next time, we're going to be using a whole different room and a whole different objects in the room. So it doesn't matter which room you're actually predicting on. Does that make sense? So the next time, we're going to be using like a completely different room, completely different objects, and we're going to do this again. So the R, we're taking the X. Again, the X is the 2D images. So R equals the X, and then the V is the viewpoints again. And the G here, all the variables I've talked about, the Z being the noise. So so I'm just going to give you an example of the representation network and the generation network. You can use different networks. So I'm going to give you some options that you can use. So these are three. Yeah.
Just for if I may interrupt, just
No.
for clarity.
Yeah. Yes.
Just for clarity, if you go back, it's probably going to be much more clear in the next slides. But so what's the significance of query again? I think I missed that.
So the significance to query the network, to query you're kind of like pinging it with what do I want to see? Do I want to be in the third row or do I want to be in the front row? Like where do I want to see? So you're querying it with the view or the position at which you want to see.
So you want
Is a position.
concrete?
Yes, and yes. So then how does it know which, like, let's say it's the position in the middle or way in the back? Like
That's
how would
the
it?
that's
So,
the
yeah.
that's the significance of it. So you can query any position, any view here. In the future, in like the coming slides, you're going to see that we can query points right next to each other, so it looks like we're walking through the room.
Amazing.
Yeah.
So then a last quick question. Sorry. So you have an R and you have a G theta. Could you very quickly take us through what's the parameters? So you have X is your input, I believe.
Yeah.
And V are the views.
V are the views, the positions, the views.
Like X, Y, pitch and yaw.
Coordinates.
X, Y coordinates, because you need to know where in the grid you are, and then you need to know your angle of rotation and your angle of rotation, like horizontally, and your angle of rotation vertically.
Per each X and Y.
Per each X and Y. Yeah.
So
it's
it's
a
kind of
big
sequential
concatenated
in that
piece,
manner. So when you say angular rotation, are we following up a rotation pattern? So is it the sequential?
Just
No.
one view, just one
Each
view.
image corresponds with a single position, angle of rotation, angle of rotation.
Say if you took your phone out and you took a picture, that's your view, right?
Yeah.
That's the position
You
at
could-
which you have taken the picture.
It's just the frame of reference. You have the frame of reference, your camera.
Gotcha.
That is the origin point of origin.
Gotcha, yeah.
And from there, in relation to that, you define the X, Y, Z coordinate. And then the rotational angle and the yaw is defined according to the camera's position.
It's
And
basically
how you-
cam coordinates.
Gotcha. And you're integrating over there.
Noise.
Are you? It's like what? Could you explain what's happening in the bottom?
Well, I have the equation here.
Oh, okay. So I may be jumping ahead.
Yeah, you're jumping
Okay,
a little
then
bit ahead.
that's
But
fine.
yeah, can we clarify some other questions first?
About the noise actually, why is it applied to the first layer, first latent layer, and why is it used?
Why is it not for the later layers?
And why is it added? Can you elaborate on it?
You're adding a noise so that you're not generating the same image over and over, right? You're adding a noise so you're generating different images every time. So it's a different noise.
So as we want to kind of get to the image which is as close as to the truth, so why should we add noise to it?
Why add noise to generate the image?
Yeah, so you're working, it's the underlying framework is Bayesian, or at least it's couched in a Bayesian space, or like mathematically. So you're kind of saying that in theory there are other images that could actually correspond with some set of things. Yes, there is for this specific scene there is an actual ground truth, but remember at certain points they actually talk about how they wanted to be able to in theory input no images. So your V1, like this point here, would have no information, and you still want it to be able to generate stuff, which means that you're going to have like an extremely high ambiguity, random, effectively guess, right? So anyway.
Yeah. Okay. You have another question? Okay, perfect.
It's not. This is an extremely simplified
So
perspective.
it's added to all of the layers?
It depends on which network you're looking at, which we're gonna talk about in a
We're
second.
going to talk
Yeah,
about it.
so these are three different examples of CNNs that you can use for your representation. They found that the tower worked really well, so for all their experiments, they used a tower. So here, essentially, all the black arrows represent convolutional layers, followed by ReLUs, and all the red arrows with the plus right there indicate the residual connections. And you see the strides and the kernels over there. So these are just three examples of what you can use.
And note that there's no noise at this point, because this is the first step. But you can see that even here, they're adding the viewpoint information at different points, and they do similar things with Z.
So what they have is they try to get a representation based off the image pixels and also the viewpoints and all this stuff. And they want
Exactly. So you see the V over there, the V and the X are being inputted. So the V is the viewpoints, and the X is the actual 2D image that you see.
This concatenation shows where they are inputted.
Exactly.
I see.
Yeah, so everything is put together. Okay, so that's the representation network. And now this is another example of the generation network. So it's a possible architecture. So you have convolutional kernels and stride size over there. Again, the letters are kind of confusing. The H is actually the image being inputted. You have the viewpoints and the representation being inputted as well.
So the H is an intermediary image. So the R is where all of the signal comes in, and then you can kind of think of this as an LSTM.
So here at the core is a skip connection, convolutional LSTM network, and you have that throughout.
But the notation is really weird because if you were thinking of this as a language model, H would be your intermediary embeddings or your tokens. C would be the actual inner state of the LSTM that's being passed between the networks, and U is the skip connection.
Essentially, you have a distribution from which you are taking the generation of the images, from which the images can be generated.
Could you please iterate over that again? So the speaker. So you have H, C, and U. What were they again?
So H is an intermediary. I'm pretty sure it's actually an image, because they actually say at one point that they upsample it. So I think it's an intermediary image. So it's the guess of the new predicted image at different time steps. So it's kind of refining that guess. C is the internal state of the LSTM.
Yeah, so you have
It's just
that.
an embedding that's being handed from step to step. And U is effectively H, but it's being dumped out. It's a skip connection, so you're just sort of like adding the previous time steps and carrying it along to the final.
It's the pathway skip connection pathway.
right? You can see on the bottom here, this is you.
I see. And X's are matrix multiplication, right?
In
the
that
diagram?
bottom diagram, yeah. I assume, I hope. It's not
Again,
very
one
well
example
explained.
of what you can use. They did upload the code as well, so I'll show you that after. Okay, so again, I'm going to show you an animated view. So you have a view from the top corner, input that into the representation network. You have a representation created, and now you have another view from a different viewpoint. Input that into the representation network. Again, populate the representation. You have the third view, hold that out, and now we're going to create a view based on the generation network. You have a prediction and you have a ground truth. So now if we take those predictions very close to each other, it actually looks like we're navigating this environment. But actually, this is all generated. These are all generated. All the predictions are generated.
So you mean the 360 angles?
All of them are generated because you're just taking 2D images and you're moving them slowly. So it's kind of like a card, like a book. You're trying like flipping it really, yeah, flip book.
Question.
Yeah.
You are querying X. What your inputs for querying is X, Y, and angles, right?
No.
No?
It's-
We're kind of skipping over stuff. It's actually you take sine and cos of the angle, so you actually split up the angle
Okay.
information again, and then you concatenate it. But that's what goes into. It's just one piece of information that goes with the image input to the representation network,
Okay.
and input, and that's what's queried.
Okay. Thank you.
Okay. Yeah.
This slide about the generation network was a bit difficult to understand for me, but sort of roughly what is happening there? Like, why is it an LSTM? What is it doing in those time steps, sort of from a high point of view? Can you explain a bit more?
Why? That's a good question. That's a good, yeah, sure.
It's basically refining the image.
Based on what?
So you remember the actual thing that we're trying to do. You want to go back? Is you're trying to really do, even back another slide. The real thing you're trying to do is build up a representation. But when you go to the next slide, remember that step's coming up in here, in R. And what you're basically doing is you're building an internal representation, Z, and you're building an actual representation of the image itself, the final viewpoint, iteratively over time. So you're sort of like, one of the
So,
things...
yeah, actually, there is a, I guess, it becomes more and more clear as you have more and more observations.
Yeah.
So you see later slides, if you only have, say, one observation, you have uncertainty, like what is actually going on. If you only see, again, going back to Block's example, right? If you only see one point, one perspective, then you don't know what's actually happening. And in the maze setting as well, if you're going through a maze, if you can't look through a corner, then you can't see that part. But
We can talk about it more in the discussion as well.
yeah.
What was the loss function for the representation graph network? The loss function that you trained that the representation.
Let's get to that. I think
you
it's
have-
the future. If there is one last function, we'll get to that. But they say it's unsupervised.
Yeah.
No, yeah.
Elbow last?
Mhm.
Maybe you should have just, or I shouldn't have tried. Pen?
I
Okay.
have two questions. The first question is the training process always 3 held out 1?
No.
No, you don't have to. Like you can input more. Like
Yes.
you can input 10 if you wanted to, and then output 1. You can do 1, input 1, and then try to output 1. But it's going to be uncertain, right?
But in that case, does that mean the representation network itself also has to be recurrent because it takes variable as input?
No.
So
So we are summarizing all the representations. So let's say that in the first iteration you're taking 3 representations.
yeah.
So you just, here they have used summation as a summarization function.
Oh, I see.
But then, it's just that what they have said in the paper and also in one of the talks, that it essentially, when you're adding, it doesn't kind of eclipse the information in other frames. So you essentially adding. So it doesn't make a difference if you're taking 10 representations or 3 representations, because ultimately you're just adding it.
Okay,
So
basically,
I think it caps out at about 30. They said it stopped. You stop getting it.
oh, so basically their input and their gradient are just averaged.
So yes, that's
yeah.
an important question, because they talked about normalization, which is essentially like taking the mean or something. But then they have tried doing this with and without normalization. So the summary function was just adding the representations, and there was another experiment where they normalized it. But then they said that it hardly makes a difference. It's like eventually the network, it learns how to develop images from different viewpoints.
Is that a point from future? So are you
Yep.
going to talk about it?
Yep.
Then let's not continue. Any other questions? Okay, maybe that's the other point I should have said.
one more.
Okay,
But
but
it's probably, very technical.
oh, it's fine. Asking technical questions. That's the point.
Okay, the second question is that is the generator always generating a sequence? Because it's an LSTM.
You're always generating the image. If you're using whatever you're using for the network, generation network, they use draw, but you can also use pixel CNN. Yeah,
But you always get a sequence.
yeah.
It's they call it, it's an auto-aggressive style. So, got it?
Yeah. So basically, they want the they want the generated image to move smoothly. So at the first few frames, it will have very hard ISC. Sorry.
Okay, so let's stop from there.
Okay.
You can come sit over here so that the mic can pick you up if you want to ask more questions. So, oh, sorry, didn't mean to. No, please do come here. I do want you to ask questions.
Yes, I'm
Yes,
not picking you on a microphone.
Damn
lead.
it. Come sit with me. Is it better now?
You're right beside the
Let's carry on.
microphone.
Okay,
Okay.
sorry, I have to pause you guys because number one, when you speak, could you speak louder? Because like if I watch from the stream, I could barely hear loud. And number two, could you try to repeat the question especially if they say like 5 minutes?
Yes. Also, one thing I should have pointed out earlier, I have to say that right now. Do not ask anything that you think is going to happen in the future, or better said, keep your questions about what you've seen so far, because they have a plan. They're gonna go through it, the entire thing.
Okay. All right. So here we have an overview of the prediction and the ground truth. How do they look? Pretty good, right? So on the left you have your prediction, and on the right you have your truth on both columns. I know the predictions are a little bit blurry, and the truth are sharper, but they look pretty good. And here we have some more.
You've
Oh,
also
shoot.
blown these out. That's
Hold
partly
on,
why
where
I
is
think
it?
they're pixelated as well.
There you go. So here we have the observation, and the rendering is what's predicted.
So basically,
Yeah.
your rendering is creating like a video.
It's creating 2D images.
Could you repeat the question?
So the question was, the rendering, is it creating a video? And the answer is, no, you're creating 2D images according to the viewpoint at which you have queried the network. So adding all these 2D images, you can create a video.
And that's based on the query multiple points, basically.
Yeah, based on the viewpoint at which you are querying at. Yeah.
We're talking about is sequential, so that's because the images are generated sequential. That's why you can kind of do
Exactly. So
like a
say if I
video, right?
generate my viewpoint over here, and I generate another one here,
Another one.
and another one there, so it seems like
Since
it seems like a video,
360
right?
angle.
but it's not actually a video.
Okay.
Yeah, just for aesthetic purposes. So now let's take it one step further into a maze. Now if we have the observations at the top, the ground truth, and the neural rendering on the bottom. So the rendering is the prediction, and the map is the actual map of the maze. And now you're going to see something very interesting. So it's able to predict what the maze actually looks like based on 4 observations. But the next example,
Are you saying only 4 observations?
but the next example, look, there's uncertainty on what the rendering actually looks like. And as we add more observations, we can see what the rendering actually looks like.
So in this
So
case, just to be clear, you're rendering a map. You're not rendering a perspective necessarily. So
That's
that
right.
rendering in this case is you're actually rendering a top-down view of the 3D space. So that you want that neural rendering to match the map on the right. It
That
is
makes
still
sense.
operating on 2D viewpoints, so it still can do this, but one of its representations is of a high-level map, a top-down map.
So it has more trouble with the high-level map than with the...
So in a position where you have lots of turns and corners, you can't see around the corners, right? Just like if you were walking through a maze yourself, if you can't look around the corner, you're not going to know what's there. It's going to be uncertain to you, unclear to you.
So it's
Same thing here.
It's like the slide that you had at the beginning. We couldn't tell if it's 2 blocks or 3 blocks. Right? We just don't have the information.
Sorry, what's the question?
This is like that slide you had in the beginning, where you
Yeah.
couldn't tell whether it was 2 blocks or 3 blocks.
Kind
Right?
of. Like,
Well, we don't have
yeah, if you don't have the information to begin with, how can you represent that information?
Sorry, so that flashlight that's sort of walking over there, is that sort of that's being generated, or there's some like
Sorry,
actual
which-
walking around and giving you observations?
Which flashlight you're doing?
Oh, this is the yellow thing that's sort of
The
walking.
yellow thing, that's the real.
That's the
the-
real. Okay, so that's
So that's the
periodically
ground
give-
truth map. And then you have your neural rendering map.
And the yellow triangle, is it how far it sees, or
It's
That's
the direction.
Just the direction.
direction and the image, yeah.
It seems that there is the example that you had about the maze. It seems that you can't construct a spatial relation because you don't have a global enough of a view to construct a map. Is that a fair comment?
Can you say that again?
So you gave an example about if you're in a maze,
Yeah.
it's harder to say what the global map is. I'm saying maybe it's because you don't know what the relationship. You see, you have local visions,
Yeah, you have
but you don't have the global. You don't know the
The
spatial
global
relation
one. Right.
relationship.
Right.
But part of what it's showing here as well is that it can figure that out, right? Because so if we watch, so we'll let it kind of go through. So this is one version where you're rendering the 2D frames. This is a version where you're rendering the top-down map. As it gives it more information about viewpoints, it starts filling in missing information about what it knows about the environment.
So more viewpoints do actually help.
When it gives information about ambiguous details of the map, yeah.
Okay.
I think part of what you said in the beginning as well, you can do a lot with this thing. They're really trying to sell GQN as like, you could do anything with this, right?
Yeah, and
so-
we'll brainstorm the applications at the end.
Yeah.
We have a quick question here.
Yes. Does the ground truth of the bird's eye view participate in training?
No,
So-
you're only looking at the observations.
Yeah, but
Hence
that-
only
But that bird's eye view is also generated.
the bird's eye view is generated. Yes.
So
You're not inputting the bird's eye view as an input.
so it is able to generate the bird's eye view without using any bird's eye as
Yes.
as training image.
Exactly.
Yes.
Yes.
Just a question from online. Do they mention the optimal or minimum number of observations to construct a complete map?
So we saw one observation. It wasn't able to complete the. As you can see, is it going? There was a lot of uncertainty when you have less observations.
I think they showed that like 5 was pretty good.
5.
Again, unless you deliberately do something that's tricky, right? Like if I put a ball behind that wall, then and I never show it that there's a ball there.
Excuse me, do you think all of them can measure to understand the complexity of the space and they say, okay, trying to
No.
have some.
When you say uncertainty, does it look like that it's blurred?
Good question. So I'll talk about uncertainty now.
Perfect segue.
So the predicted uncertainty is measured by computing models' predicted information gain at each location. So we're averaging over the 3 different heading directions. So you can see, okay, let's see here. Yeah, so the more, so if we were to, let's see.
It's basically the heat map.
Yeah.
So the colors would indicate the bluer the color, you're talking about more certainty in that the prediction. And this actually answers also the online question. So if you can see that with 3 images, the bird's eye view has more certainty. Looking at the heat map, you can say that, you know. But again, it's very situational, as in depends on what you're talking about, and I mean it's very difficult to say that 3 is the exact number or 5 is exact. Yeah.
Yeah, exactly.
Yeah.
Just curious, how did they measure the uncertainty, the images with persistence?
Information gain.
Roughly, information gain. Sorry, I'm overstepping. Facilitator.
Go ahead.
Roughly, information gain is the amount of information that you will gain to perform better, given a sample that you receive. That's the intuitive way of saying it, but it has it's based on an entropy-based measure.
But it's not the complexity of the scene. It's just how unexpected something was or wasn't, or how much. Yeah, you know. Yeah.
Yes.
Okay, well, on that idea, there was another element that they found that GQN is great at. So here we're clustering based on the rooms that the objects were in. So as with VAEs, you can see that it was pretty much clustered based on the horizon, like the wall angle. I see these 2 wall angles are very similar, hence they were clustered together. But they weren't the same room. See, these dots here are different views, and the colors of the dots represent the room that they're in. So if we have a blue dot here, that's in the same room as the blue dot over here. They're not clustered together. So the VA, like this, failed to do that. And because the information was lost on the ground, and it was lost on the wall angles here. But with GQN, it was able to cluster based on the rooms. As you can see, the same colors or the same colors of the perspectives from the same rooms were clustered together. And you can see these 2 images, like these 4 over here on the side, on the right, they all had the same images. They all had the same objects, but they were from 2 different rooms, right? And then it was able to correctly cluster those. So that it's really amazing how you can...
And encodings in general have been missing that information for a long time. Unless you want to use capstone. Sorry, I couldn't resist.
No, but it's a good point. I think that is actually the point.
That's amazing.
So I'm thinking how to word this. So I thought at the beginning you were feeding it data based on which room it was in. No? Are you feeding it pictures of rooms that are totally different and then it automatically tells which room it's in? Or I thought right at the beginning when you're creating the different functions, the general function for each room, you're telling it which room the initial stills are from.
So so you have to kind of think of it as like, how would I actually tell it what rooms the images were from? So there's no vector, there's no encoding that basically says, this is room 10, this is room 5. That's never input to the system. The only way in which you're kind of telling it it's the same room is that during training, you give it a whole bunch of viewpoints from the same room. That's just the way you do.
So right now, as you can see, the same colors, we gave it 1, 2, 3, 4, like 4 views from the blue room on the GQN side, right? So these 4 views, and we put it through the representation, and they were clustered together. But if we do the other way, they weren't clustered together. Does that make sense?
So at each training point, right, at each point in time, that you're training, if I may say that, or you wanted to make an inference, your input has images. Each sample of input has images belonging to only one room, right? Then you move to the next data point, then it's another room. You don't mix the images from different rooms and ask it to predict a third image.
But right here, we are giving it the same rooms, just to look at the representation.
Yeah.
So right now, we did it just for this purpose. Forget about what we did before, but this is just for the purpose of comparing GQNs and VAEs.
Let me try one more time. I don't think I get it. When you give it the initial training data, are you giving it only for training it on only one room?
No, it's about 2 million rooms.
Okay, many rooms.
Yeah.
And then when you do the backpropagation comparison, you're again you're comparing it to that room, or it's
the room doesn't matter.
It doesn't matter.
The room doesn't matter at all.
Um,
When you're training the network, the room doesn't matter.
Totally, it doesn't.
Yeah,
care
it's
about
just
what
about
room
the observed
Okay.
viewpoint and the generated viewpoint.
Okay.
Right. That's how you're training the
the
network.
But in property of the end result of this model is a grouping of rooms, which is very interesting. Okay.
Exactly.
Yeah.
That's the key point, yes.
So why VAE loses this amount of information versus GQN? What makes it so powerful? What GQN?
Well, I mean, okay,
Can you repeat the question?
Sorry.
The
can you
question
repeat?
was, what makes GQN much more powerful in terms of getting the information versus the VAE? What is it based on?
What is it based on? It's clustered to. What did you get to me?
What causes this phenomenon that the cluster is much better?
A standard VAE. So the question is, why is a GQN better? There's a million reasons. It's way bigger than a standard VAE, but like the most obvious thing is, remember, the viewpoint. The VAE doesn't have the viewpoint, or if it does, it's
It's not a fair comparison because you haven't provided input.
Okay, that's argumentative. I'm gonna stop you.
But it doesn't matter, right? Because well, actually, I must have the viewpoint on some level, because else. No. I'm pretty sure it doesn't. It's a standard VAE.
So
But we can discuss it after.
yes, we will.
But good question.
So clarification question for the pool moderator. So so you're saying about the comment that you made earlier. You said that the room doesn't matter, but at each point in time, you're using backprop, right? So during training, at each point in time, you're giving it, say, two views of something. That something has to be one room, right? You can't give one view from this room, one view from
Yes,
that room.
exactly.
and
So
it's-
per
So,
iteration, it's the same room.
So then you are implicitly informing the network. It's not magically happening.
But
You're
say-
implicitly informing the network. It's implicit that these two are from the same room, and also the third one, you're implicitly querying it to be like it can't really generate. If it generates something from another room, that's not acceptable, right? So we expect it's not this is expected to happen, like hopefully, right? Is that correct? Does that help?
That's kind of what I was thinking, right? Like at the beginning, your training data is related to your like they're the same room.
So it's
So I would
implicitly
expect it to be
informed. Yes, but no explicit way we're actually saying, oh, this is one room. Remember, that's implicit. How we're feeding the data.
Question then, we would expect the same clustering effect if we shuffle the images or not?
Wait. Yeah, what do you mean by shuffle the images?
If
Yeah.
the data points are coming in a different order, I don't expect any.
Yeah, exactly.
So like showing the room A first, then room B.
No, it would not. It wouldn't matter. It should be independent.
So that's the key result of the improvement on GQN, actually.
In the sense, is what you're trying to say is that there's no explicit ordering to the images as they're input to the network.
Yeah.
And therefore, it must be inferring any ordering structure. Yes, that's true.
Okay.
Yes.
Thank you.
I'll be very short on this. Actually, the key element here is a human level intelligence that we're talking about.
Yep.
So it's like, taking a baby to different rooms and showing the baby different rooms. So in every iteration, what we are doing is feeding information about one room. So in a sense that you develop a very generalized probability distribution, or I would say that a generalized understanding of how the light would have an effect on the pixel distribution. So that's how the order doesn't matter. So just like you take a baby and take the baby to different rooms, it's not like the intuitive understanding that the baby develops at the end does not depend on the order in which you're showing the rooms, right? So it's the same thing. Every iteration, you're trying to train the model to understand the ocular effect and other pixel distribution based on light, and then you're using it at the inference time, you're feeding any random room and it's giving you the viewpoint. So that human level intelligence, you're developing it, and that's exactly why when you do the Tasney plot, you get this, it has a semantic understanding of images belonging to a certain room. So it's clustering based on a room because it has developed an understanding, a human level understanding.
Okay,
of
disclaimer, humans do more, but let's move on. That's argument. You said that like the last time you didn't say that, I wouldn't say anything, but you said that 3 times.
I'm sorry.
Okay.
I'm sorry.
It's good. It's good. It's good.
So another unexpected but welcomed perk of GQNs is generalization. So they trained, this was an experiment they did, trained on spheres that were never red. And then they trained on red objects that were never spheres. And then they showed the network a red sphere. So that was a target. And it was able to reconstruct a red sphere. So this tells us that the generalizability of the network is great.
But yeah, we'll talk about it after. I'll get excited if I.
You want to get it out.
No, it's okay. We'll talk about it after.
So it's seen other color spheres, but red it hasn't seen. You
Yes.
showed
So it's
red
great.
sphere.
Yeah, exactly. So it's generalizable.
How do you query that? I want a red circle. How do you query that in the system?
You show it
Can
a
you repeat the question?
red
How do you
sphere.
query the
How
red
do you
circle in
how
the
do you
system?
query a red circle? So you just input a viewpoint, right? You input the observation and then you input a viewpoint. So you input a new observation, and then out of this room, and then you input a viewpoint at which I want to. So you look at this red circle from this side and say, what does this red circle look like from this other side?
You have already created representation for the room. Now
But you
put a
didn't.
new
But see,
object.
you created representation on everything else except for the red circle. So this baby has never seen a red circle before. So you tell it, okay, well there's a red ball here. This is what it looks like from the left. What does it look like from the right? Going with the gray. Going with the gray.
Works as an analogy.
Yeah.
But the key point is, remember, we can always go, regardless of what we train the network on, we can always go from image to an embedding space, to a representation of the image. So if my target is that red thing, I can just put that image into the thing and it'll spit out a representation. But it's never seen that. So that representation, if it didn't learn how to generalize, would be meaningless. It should just encode arbitrary stuff, right?
Okay. Yeah.
So that's
those
the
are
baby
the-
seeing it. We can always input an image into the network.
So those are the perks of having a GQN. And now applications, you can imagine using autonomous driving or seeing one view and you want to see what the other people are seeing. That's one. For game applications, if you want to create a game world, right now it's very expensive to draw out the entire world, but if you can just draw out, say, 2 views, it will generate the rest by itself. And same applies to VR and AR applications as well. You can draw, you don't have to create the entire space, but only certain views of it, and it will create it for you. So we can discuss other applications later, but right now, so the authors of this paper did an internship with using this representation for RL training. So they observed more data efficiency in policy learning. The convergence levels 4 times fewer interactions than a standard method using raw pixels. So they didn't go into too much detail about this, but I just want to show as one example. And the code is here as well. They uploaded.
Sorry, if
Yeah.
you could go back to the previous slide.
Yeah.
You have a fixed camera, you have a moving camera. Could you elaborate a little bit more what's happening?
So this was very quickly brushed over, but yeah. So they had a.
Actually in the paper.
But there aren't much details in the paper.
No. So that's just one application of. So it was trained quicker.
Okay, it seems that the curve is a little bit, like it's harder to learn when you move the camera, which is not unexpected, right?
Yes,
From
Yeah.
the graphs.
because it means you have to also handle the stability of the background.
Okay. So the code is here. If you want to check it out, there's multiple different environments. Yeah. Now we have a break. Yeah.
Absolutely.
We'll go into discussions. Okay, so before we jump into the discussion questions, does anybody have any other applications that they want to, or any questions first of all? Yes.
Okay.
Yeah.
So, because I'm loud enough, I should give others a chance also. So you did mention, a good question was asked earlier, like what's the loss? You did mention it was elbow. Elbow is usually a proxy for KL divergence, or it's technically KL divergence. What are you comparing with what? So because you said that you're not using ground truth. How are you training again? I'm not entirely clear on that. So you use the loss. What are you back propagating to? Or better said, what are so you have how do you compute the loss between which two pictures?
The predicted and the ground truth.
So it's
that
reconstruction
sounds
error.
supervised.
It does sound supervised, but I could have sworn they said it was unsupervised. So it may be that, well, if you think about it, it's the representation layer that's unsupervised. Because
So that would be more, because then you say, okay, but you don't have a representation as ground truth. Your ground truth is an image, right? And it's not your architecture didn't look like an autoencoder. So then how is it a reconstruction loss? If you can go back to the...
it is an autoencoder.
It
so
is?
it,
Okay.
yeah.
Okay.
So there's an inference LSTM as well, which we didn't talk about.
Right, there's, yeah, there's
Yeah.
that one.
It's so I actually think that it actually does function more like an autoencoder, but the thing is that it's very, like, the network is extremely convoluted, not convolution.
I get you. You use that a lot.
So there is actually another LSTM that can go from an image to a Z value, I think. And so you can do image to image from these. So you can do.
So you want the encodings that you're getting from your ground truth to be similar, hopefully, to the encoding that you get from your first network. What was it? So you had a generator and
They call it an inference network.
Inference network. So that's why you're using elbow loss.
Yeah, so you have a reconstruction loss, and then you have a tail divergence over the Z values. Or no, yeah, over the Z values.
Oh, so you actually do also have a reconstruction loss as well.
You have a reconstruction loss and a tail divergence over the Z values.
So,
you
be
have
more
to
specific.
require
Or is it this?
distribution for the ground
I
truth,
think
right?
it's like you have the
Ground truth
you're
distribution.
learning
Oh,
the
right. We should go to
distribution
the...
using the Z
Nice parallel
values.
discussions.
Hold up.
Okay,
And then
let's not
you
have
have the
parallel
two
discussions.
distributions.
Experts,
So you
experts,
compare.
experts. You're not
I'm
supposed
chewing
to
you
have
out.
parallel discussions.
Yes, sorry.
Okay.
We got it.
And Parham, you're being broadcast live. Parham, you're not supposed to have parallel discussions. All right, please carry on. If there are other questions.
Any other questions?
I mean, just following up on that, like, in the end you have a ground truth picture and a predicted picture. Like, do you actually take a loss function, so it's like L2 loss between the pixel values? Do you actually do something like that or not?
Yes, let me double check though. Give me a second.
So maybe we'll talk about that again. Mike will explore that.
In my 57 page video.
Okay.
Please carry on.
Okay,
One more
well,
question. Actually, I'll wait till the end of the discussion.
okay. Let's go to the discussion questions then. Shoot. So building upon an internal representation, Mike, this is your question. Using LSTM and an unusual approach in the image domain, the authors argue that it allows the representation of much more complex domains. So what are the limitations of this approach, do you think?
So you're actually, the LSTM is actually building up an internal representation at both the Z value level and at the in terms of the actual output image over time steps. And so my pitch was, I mean, really, I was thinking about this actually on the way over here, and you can actually think of this as being a really weird way, or a very different version of almost what a transformer net does for in a linguistic context. So the switch is that in traditional recurrent models, you think of your tokens. You think at the token level. So I have the previous token, and then I input that to the LSTM, and I get the next token, and so on. Whereas with transformer, kind of in the transformer context, you kind of think of the whole sentence almost, and you have all of your different tokens at the same time. Well, an image, in a certain sense, the different components of an image are kind of like your tokens, and you're generating the entire image at the same time, right? So what the LSTM is doing is, in a certain sense, is it's kind of like taking your image, building up a rough estimate, then you input that rough estimate of the entire sentence or the entire image back into it, refine that, put that back into it, refine that, and so on. So it's like an iterative way of doing kind of almost like what the transformer does in a single step. Or the multiple transformers you could almost think of as being like an unrolled LSTM. Right? Does that kind of make any sense, or am I waving around in circles here?
So, like, my understanding was, so imagine this images as the tokens, and then in the NLP work that we try to get the context, infer the context. The context in here is the 3D representation that we try to get.
Yeah.
So this is the analogy between these two, is that correct?
Well, so there's two things I'm saying. The first thing is that we're switching from the image kind of is almost like functioning at a sentence level. So you're switching to a sentence level, one. And then the second thing is that what the LSTM is doing is basically refining the entire sentence at the same time, right? And with transformers, you're doing a similar thing. You're refining the entire sentence at the same time, except you don't have to do it in a recurrent way. You do it all at once. Time step, time step.
So have you tried this transformer?
No, this is a different
just
literature. I'm drawing a
analogy,
parallel,
yeah.
right? So what I'm really saying is that if this model seems to be working better in the language domain, and with this example it's working better in the image domain, is this actually just like a better way to actually build representations?
Okay, so a couple of questions. I feel guilty. I stopped you, so maybe you ask questions.
Okay, so in this case, what's the sequence here, and is it possible to visualize it?
Exactly.
Okay, good.
So from my understanding, the sequence is just an increasingly refined image.
Yeah. From the same point of view.
From the same point of view.
And the only last one is the end result.
Yeah, but you could stop earlier. And in the training thing, I think if you go into the minutia of how they're training, they'll actually compute an error gradient over multiple of the intermediary steps as well.
Okay, so does that mean if we replace that LSTM with a group, it just looks like a residual network?
I don't remember GRUs enough, although I was technically at the classics paper, which we'll plug. So there's another video on it, another AISC video on the GRUs. ACE view on GRUs, but I think you could sub them out and it would work. It should work.
So GRUs aren't that different from, they just have one less gate. Well, there are other architecture differences, but they're not, so GRU and LSTMs are not really that similar to ResNets, but you can add residual paths in GRUs and LSTMs, and often people do that as well. That could be the only similar.
Yes.
Similarity.
But my point is that their only difference, their biggest difference is one of them is vertical, and the other is horizontal.
Between what and what?
The difference between residual network and GRU.
Residual networks are used in they're CNNs, right?
Yeah. Yes.
ResNets are CNNs, and GRUs are recurrent nets. So there are a lot of differences.
So
that's not the only.
Yeah, that's my point. One is horizontal, and the other is vertical.
Let's move on from this topic.
Yeah, that's fine.
Yeah.
Well,
Let's
one question about the previous. So how do you know this recursive procedure? How do you know when to stop? Is it just like a hyperparameter? You say, okay, stop after 100 iterations, or do you at some point does the model see, okay, now it's a good picture. Now I stop. How does that work?
Yeah, I mean, 5 observations is pretty good, but yeah, you stop when you get a clear picture.
You know what I mean? How does the model know, like, okay, now I'm done. Like I've done this LSTM 1,000 times. Now I know it's good.
It's an arbitrary stop point.
That's arbitrary stuff.
I think they toy with it. I can't find where. Again, it's a 57-page paper, so I think they toy with it, but I can't remember where the difference is.
So I don't see how early stopping is relevant, but you don't want it to move on. So maybe I'll ask it later. Sorry.
This is me again.
Okay, we can go back to. Okay, Ramia's question.
Let's do that.
So now think about generating text pertaining to some topic with different viewpoints, like perspectives of text. Can you imagine how GQNs are useful in that context?
No. Can you?
Yes.
Yes.
How?
So
Let's give everybody else a chance first.
So as we had this, we try to predict the other word in the corpus when you have this word. Like you assign a probability to each word by the prediction that you have these images. And I guess that would be the same analogy.
Okay. Think about different viewpoints, like different views.
Viewpoints would be the position of each word in the corpus in the sentence. Is that?
Okay. Okay.
So we were thinking about this. So let's say that when you talk about any topic, there are different perspectives. Those are the viewpoints. So for example, let's say that you have the topic of taxation, and then you want to know, like you are giving it the capitalist viewpoint and the socialist viewpoint, and then you're generating text from a totally different perspective, somewhere centrist sort of approach where you're neither towards the right nor the left. So that's the kind of viewpoint I'm talking about. So generating the entire text on a particular topic based on a particular viewpoint.
There's multiple things that you want to do. First, try to capture the whole context through this viewpoint that you're trying to say. Then, generating a whole topic and in their sequences, that's, I guess, a lot. Yeah.
Is that something that was done?
No, it's
just ideas. These ideas were.
I was influenced by. I mean, I was inspired. That's the right word. Inspired by, the seminal, work that went on this particular topic, and they were saying that images can be replaced by anything. So why not replace images with text? Because we could use the same LSTMs, we could use the same, some sort of embeddings and all. We have so much of, analogies that we could draw. So why couldn't we use it for, defining different viewpoints?
It's like having this word to vec, but instead of word to vec, we are trying. It's like the same architecture as word to vec, but in here you have this small context. In here you provide the whole LSTM structure on that. You generate one, and then you have this.
I think they're speaking of like a bigger granularity. They're talking about viewpoints and
like literally like political spectrums, like right, left.
I think sentiment analysis would be a much easier starting point. The same text with a different sentiment, but
why I thought about this was because the loss function, it kind of reminds me, the elbow function that we're trying to optimize here, it kind of reminds me of LDA, because in LDA we are doing the same thing. Given the distribution of words and given the distribution of topics within the document, you are trying to learn some sort of Q distribution, and given that you have the true distribution P. So here, given the representation, given the viewpoints, you have some true distribution, and what you're doing is that you're feeding in these Z's and trying to learn some latent, representation of different things. So from that, I was like, okay, it could be used for some sort of, you know,
Expand
way
the
of-
idea of viewpoint to the whole thinking ideology of a person, actually. It's
Exactly.
That's amazing. And that's interesting. Actually, in the early 20s, there was a literary current called Cubism that was trying to imitate what the painting was doing. So these stories had the same landscape with one actor describing the view, the second actor describing his own perspective. It would be interesting if a third actor synthesized with the first two telling the story, right?
Yeah, yeah. That perfectly makes sense. Yeah.
Yeah. Okay.
And just maybe kind of like a counterpoint. I know it's kind of everyone's being really optimistic, but like something that seems to me that would kind of stop that from fundamentally being possible is that when you think of like every single dimension of information you're being put into this network, all is related by space, right? Like that when you're talking about like X, Y, Z coordinate, or even the pixel location, like in the object that you're representing, they all are in the same, like, I don't want to say like dimension, but in the same kind of, they all represent the same core concept of space or location in space.
Visual restrictions as to how far can you.
Yeah, and when you're trying to relate the, let's say, the topic to, let's say, the representations of different words or however you like represent that, because there's no connection between the underlying like dimension or things that it's representing, I feel like you kind of first be limited by you'd only be able to put in one dimension of let's say political spectrum, because different ideas that you're representing wouldn't be able to like be in that same space of input. But I don't know.
So you had the representation, it had an X and a V element.
Yeah.
I don't think it's hard to get the X because you have word embeddings and other things, you can get it. But I would agree that the V would be the most challenging thing to get, because here how would you numerically define or algebraically define conservative viewpoint or liberal viewpoint? So how would you do that? That's the challenge actually. But you have raised a very great point. So within that R, X is easy, but V is tough.
I would try to add to his great point that it's the difference between Euclidean space and versus non-Euclidean space. In the Euclidean space, that you have this, each entity has the relation between each entity is determined. So you have this space. You know that, for example, what is the unit of distance in here.
Yeah.
But in topic domain, you don't have you are in the realm of non-Euclidean data, which are like graphs, and I have this representation in 2 days from now, which I will definitely talk about. Yeah, it's about GCN, so I would definitely ask you to watch it.
Tune in on Wednesday.
It's Wednesday, 12 to 1.
Wednesday at noon. Tune in for
Lunch and learn.
non-Euclidean spaces.
Yes, GCN. We talk about non-Euclidean data, how it works, and so on.
We should charge for advertising.
It's our own event. Okay, so I think the consensus is so like just to sum up what was mentioned is that it seems that sort of visual cues can be more constrained spatially than sort of topics and texts, which can be a little bit more volatile. But I guess the counter argument could be that well, these are simple, simple shapes that we studied. Like this image can also get really complicated if you count in, high resolution images of what's out there, like in the world. Like you don't know if you look left, are you gonna see a tree? Like you probably can guess you can see a street, but so I just wanted to put that out there.
Okay. Thank you for that summary.
You're welcome.
Yes.
I have a question.
Yeah.
I was actually expecting Chris to ask this, but yeah, we're going to do it.
Wait.
So the question is, does it have built-in rotation equivalence, or it just augment the training data to the extreme and just buy more machine because it's Google's money?
Sorry, what was the question?
What does it have built-in rotation equivalence? I mean, if does it need to rotate the location and orientation of the viewpoint and the 3D model at the same time and feed into the same network again, and well, to get an unbiased result, or the network structure can already handle this?
Well, so this is, should we plug the other talk on location invariant?
Yes, please.
So there was another talk on that, and I think in that context, the idea was, can you build up an internal representation that has the sort of non-linearities of rotation structure, or like rotational structure, or rotational invariances encoded into the representation. And how does that relate to what we're doing here? The difference between those two approaches is that because we have the embedding for the viewpoint, because we have a way of representing viewpoint, you kind of, it's almost like you're cheating on rotation, because rotation doesn't actually really exist.
Yeah.
It exists as a series of parameterized location, like viewpoints,
Yeah.
which we know is a rotation. But in some sense, the model must understand it implicitly, otherwise it would get it wrong. But like, you couldn't be like, model, here's this image, now rotate it. There's no sense in which that's askable, right? Except by saying, I want you to give me this set of viewpoints in a circle,
Yeah.
which I know is a rotation. Does that make it sense? Does that sort of answer your question?
You're just changing the viewpoint. You're not. If you change the model and you change the viewpoint, you're still changing one. Does that make sense? You can keep one the same.
I agree, it is kind of cheating, but in the meantime, the input, the encoding of the input always had an explicit meaning that is like, for example, if you are given the direction of a camera, if it is facing north, then the neural network already take the north direction as an input. In this case, if all the input you feed it are facing north, and in the test phase you suddenly give it a task that where the camera is facing east, and if the network is unable to generate this, the network is unable to rotate in the test phase, then that means it's not as efficient as it could be.
I think we're talking about like edge cases right now, so maybe we can save that discussion for later.
we can talk about it after.
There were two other questions.
Oh,
Can we talk about?
Well, this is inspired by her question with the centrist and the capitalist. And the other area is application. Let's say I want to build a deck in my backyard.
Mm-hmm.
A deck. You all know what a deck is, right?
Yeah.
And you feed this thing multiple examples of deck, right? And the viewpoint would be from my house. So I show it an example of a deck of your house, their house, my house, and then I say, hey, give me an example of what the deck would look like from my house perspective. How would it accomplish something like that? And it would in this case, it's just an image, and like what he said, it's just the dimensions are just R and theta's and angle, right? In this case, we want to come up with a deck that is mechanically sound and all of those other parameters. How would something?
So you
like
want to
that
generate
work?
a deck.
Yes, and not just
Okay.
a picture of a deck, but a deck that I can get past. That is
Regulations.
safe, and I
Right.
won't get sued if I
Well,
follow
you would
it.
have to encode all that information explicitly or implicitly into the model, right? And right now, we're encoding spatial information, but we have no sense of structural integrity or anything like that, right? I think, as Ramya mentioned, the idea is that it's deriving additional information that we're not really giving it a lot of stuff about. It's only very, very implicit in the framework. So maybe the best comment would be that if your images somehow speak to the structural integrity of decks, then maybe the model would be able to infer those properties about it. But I would be very skeptical.
Can I?
I think there's other questions, but do
the other.
just so that everybody does.
What's your question?
I guess I just had other thoughts of applications. One was, like we're talking about an X, Y, Z, so I guess the next dimension is time, right? So, and your viewpoint is like an angle right now, so maybe your viewpoint could be like a geographical location instead, you know? And so maybe you could use this to look at boundaries on countries over time, over all of it, like long history, and infer unknown country boundaries or something like that. Or traffic patterns or at a subway station, the amount of people walking through, use it for historical data, fill in gaps in time, I wonder. That was one thought I had.
Generate the evolution of a new species.
Something like that, yeah?
You have to have the data, though.
Yes.
We have to have the
That's when
training.
you're moving through the time-space continuum, so you want to predict everything possible. So I guess that's too ambitious, isn't it? The project is...
So I think what you're trying to say is that perhaps, are you picking me up? Perhaps visual data are more, like the images that you're seeing here are much more constrained, like their geographical shapes and stuff, right? I wonder what your opinion is on that as opposed to time, like a lot of things can happen through time, right? Yeah. But this seems to be sort of very, very sort of basic spatial information.
Yes.
I was just thinking, do you think that that would work? Like, is that something that you think this application could do? Expand it to another dimension, to the
Yes.
dimension of time?
I think, if I'm not wrong, in Japan, they are trying to use GQNs and the additional temporal element, they're including that. So it's like if you're aware of the problem in Japan of aging population, so predicting some sort of eventuality that could happen with old people. So they are doing this. So the additional element that they include is the time element, and they try to predict whether in the future frame the person is going to fall or not. So they are working on this additional element, that is the temporal element. I heard that they're doing that in Japan, yes.
Isn't that a physics problem where you look at the person or the person standing and the next step?
Yes. And also, I saw a video where, you can only see the person doing something, from the back, and they're trying to predict in reality what the person is trying to do. So, I mean, it could be something dangerous. It could be something, probably not ethical. So, just by looking at the back side, they're trying to predict what the person is doing from the front. So that's also one of the applications. And also, as I said, the time element, they're, of course, they're trying to include that in the GQNs. And that experiment is going on in Japan, yes.
Well, I have a point.
So, sorry, Chris actually raised his hand like 5 minutes ago.
Sorry about that. I was trying to get an understanding of when you're talking about the generalization of being able to understand the color of the red sphere. Were there any examples of like what perspectives it was used to be able to generate that reconstruction? Like, I'm trying to understand whether just as an example, if they took let's say 4 shots directly looking at the sphere and just trying to find something in between all that, to see whether it was just maybe being able to look at a small perturbation of the viewing angle, or was it a very significant
A lot of red spheres, right?
Yeah,
I don't remember how many red spheres, but they inputted at least one image of the red sphere. I'm not going to tell you how many because I don't remember, but yeah.
It's more about the representation, right?
That's
the key point, is that there's no reason, it's capturing a joint distribution, which it's never experienced, and so it means that it has to take elements distinct elements from other scenes and recombine that
Okay.
distribution. So why would that matter? Well, if you have a highly coupled elements of the distribution, so if you're not properly making independent properties of the distribution, then when you when you try and represent this structure, you should get additional artifacts that have been attached to those representations as well. So in this case, you would expect that the shape information should not be independent from color. Like, why would it learn that? They won't learn that, for example. Like a variational autoencoder won't learn that.
Okay.
So when you would expect, really what you would expect to happen here is that this should actually become a bit more cube-like, or another shape.
Yeah.
But it's not. So when you're inputting that image and it's producing a representation, and then you're spitting the reconstructed thing from that representation back out, somehow it's actually it's got a notion of circle, and it has a notion of red, and it's able to actually combine them in an independent way. Does that make sense?
Yeah. Then, oh, sorry.
Go ahead. My point was different from this one.
If it's a follow-up.
It's a follow-up. Yeah. Then, why didn't you choose to draw the sphere blue or green? That's what he knows. That's what the model knows.
Yeah, so I mean, it could have gone the other way as well. Yeah.
Yeah.
Instead of doing that, it could have been, well, instead of it being blue, really what you would expect is that it would be like purple, or like some, like it's trying to do red, because remember it's RGB values, right?
Mhm.
So you would expect, so that red is some level, some intensity where the R value is higher, like when you're getting to the minutia. So you would expect that it would skew the values towards what it actually had seen.
It actually is a little bit more purple.
Yes.
I don't see red very
It's a
well.
little darker than the other red.
So
It's also flatter, the color, the gradient
It's a
on
little
the
bit
shadow
more
is a bit weird, and yeah.
What if you had given it a bunch of stripe balls?
I have no idea. It's a good question.
Try.
Okay.
Parham, did you have a quick point?
It wasn't quick, but I tried. The point about this temporal thing that you mentioned was actually quite fascinating. But I thought like the problem would, not the problem, the challenge it would face is that they are all based on probability, right? And the probability is the idea that okay, something has happened in the past, and then we get an information from it. But when you have these temporal things, there are lots of things that happen that are uncertain. For example, we had this first time that the economy collapsed in Great Depression. There was no idea about it in the models, and there was no idea about it in the data. So we just head towards it. Or when you have this sudden, for example, I don't know, accident that happens, you don't have knowledge about it, and you don't have it knowledge in your idea about the world that could happen at that point of time. So when you use this temporal things, when it has happened before that, I guess they could come up with good predictions, but they cannot predict uncertain stuff that hasn't happened at all. So because they're trying.
Gotcha. Thanks for the comment. We're almost out of time.
Okay.
Let's thank the speaker and the experts.